Section 3.6, Zeros of Polynomials. A polynomial of degree n has the form as in this equation. Here ai's are called the coefficients of the polynomial p, and an, the leading coefficient, is non-zero. In this section, the objective is to find the zeros of the polynomial p. Let's begin with some theory on polynomials. Fundamental theorem of algebra says that every non-constant polynomial has at least one root, possibly in the complex field. Here, each root will make a linear factor in the polynomial so that we can rephrase this statement as follows. Every non-constant polynomial has at least one linear factor. For example, quadratic polynomial has at least one linear factor, but the other part must be again linear factor. And so that quadratic polynomials will have two linear factors. Now for cubic polynomials, they have at least one linear factor, and the other part, quotient, must be quadratic, and quadratic can be expressed as a product of two linear factors, so that eventually the polynomials of degree n can be expressed as a product of n linear factors. Here, this is a consequence of the theorem. A polynomial of degree n has exactly n roots in the complex plane when we count the roots with multiplicity. That is, there are unique complex constants x1 to xk and unique integers m1 to mk, such that the polynomial of degree n can be expressed in this way: the product of linear terms and the multiplicity m1, m2. If we add them, then it must be n. So a polynomial of degree n has exactly n roots in the complex plane. Localization of roots. All roots of the polynomial p lie in the open disk centered at the origin and of radius of rho. That is 1 plus 1 over absolute value of the leading coefficient times maximum of other coefficients in modulus. So once we try to get roots by using iterative algorithms, then we can initialize the roots inside this disk so that we can get better convergence. Uniqueness of polynomials. P and Q are two polynomials of degree n if two polynomials agree at x1 to xr with r larger than n and distinct numbers, then the two polynomials must be the same. In particular, two polynomials of degree n are the same if they agree at n plus 1 points. So values of n plus 1 distinct points will decide a polynomial of degree n uniquely. Here we have the bonus method, known as nested multiplication and also as synthetic division. the Horner's method can evaluate polynomials very efficiently. Let's try to evaluate P of x at x equals x0. We'll use the remainder theorem. The theorem says here, P of x, that P of x is this one, okay. P of x is divided by x minus x0, then we have quotient and remainder. R must be a constant because divider is a linear term, a linear function. But R can be decided quite easily when we plug x0, then this will be 0 and R. That means P at x0 is R. So we have here P at x0. Now we'll express Q of x explicitly as in this equation, Bn x to the n minus 1 plus and b to x plus b1. We plug this here and expand. And we have here the nth order polynomial, and we have another one here. Now we try to compare quotients of equal power of x. And then we can have here n plus 1 equations. This one came from the quotients of x to the n. The next one came from the coefficients of x to the n minus 1, and so on. Now, we have these equations, but the shape is a bit different, so that we try to make the shape. Okay. Now, here, we try to add x0 and bn plus 1 with bn plus 1 0. Then this whole thing can be expressed using that way. Of course, we have to introduce over there another notation. There's b0. Then this n plus 1 equation can be written in this way. Here, bk is ak plus x0 times bk plus 1, all the way, same form. So by using this recursive formula, we can get all b values, and the last one, b0, will be the desired value, p at x0. So we can implement this one, but we have to start with pn plus 1 equals 0 and initialization, and use this recursive formula. Okay. Now, here, if we try to use table technique, then it is known as synthetic division. I believe you learned this one from high school. Now, here, the coefficients are collected and go down to become Pn, that is x0, and we multiply these two and put here and add them. That is exactly this equation, and multiply these two, put here and add them, and so on. Then, and after addition of this one, that will be b0. This is the last equation, which must be p at x0. Let's see this example. Use the Horner's algorithm to evaluate p at 3, where p of x is given in this equation. Now, x0 is 3, so we put here 3. Now, we collect the quotients of the polynomial, 1, minus 4, 7, minus 5, minus 2. Now, this an go down to bn, and multiplication is 3, and put here and add these two numbers to have minus 1. Again, multiplication and addition, and now the multiplication 12, addition must be 7, and multiplication is 21. Now addition becomes finally 19, which is P at 3. And here, this one is the coefficients of QX. Now B values are the coefficients of the QX, so that here this one is for the QX x cubed 1, and then minus 1, there's 4 and 7. So that the P of x can be written here x minus 3 and Q of x plus the P at 3, which is 19. Okay, now so that we know how to evaluate the polynomial value efficiently. Now, when we try to use Newton's method for finding an approximate zero of the polynomial, then the iteration is happening in this way. Now, P at the last point and divided by P at the same point, P prime at the same point, that must be here subtracted from the last point to get the updated point, the iterate, so that here we have to know how to get this value efficiently. And already we know how to get it. Now we'll consider now how to get this value, derivative value. Okay. Here, now for that remainder theorem, okay, from this one, now we differentiate it, then this will disappear, and here we have now, okay, by using product rule, we have Q of x and x minus x0 and Q prime x. Now, what we have to do is evaluation of a P prime at x0. So once x is x0, then no matter what it is, this term will be 0. So that it is the same as Q at x0. So the evaluation of Q at x0 becomes the desired quantity P prime at x0. That makes such a recursive twice application of Horner's method. Now, for the polynomial we considered earlier, example, let's try to evaluate P prime at 3. Then already we know that this portion, and from these coefficients of polynomial at 3, we do here the Horner's algorithm to get P at 3. Now that's Q of x. And now here, by evaluating Q at x0, we can find the derivative P at x0. That means that for Q, again, we have to evaluate the value at 3. So we apply one more time the Horner's method. So the coefficients go down, multiplication, and put here, and addition, and multiplication, addition, and multiplication 30, addition 37. The value 37 is Q at 3, which must be P prime at 3. Okay. Now we can implement the Horner's algorithm to evaluate P at 3 and P prime at 3 for the polynomial, this one. Okay. Now this is Horner.m, MATLAB code, M file. here now Horner will get the quotients of the polynomial. Now it is now increasing order rather than decreasing. This is the decreasing order. Now this is increasing order. It doesn't matter, and you can use the array either way, but this M file is made along with the increasing order. And x0 is the evaluation point. Now here for this one, and first we initialize, and then now I is moving from n-1 to 1, decreasing, and then here d at the last moment, d will include the derivative value, and here p will have the polynomial value. So you can check this algorithm and step by step, and yeah, so that you can make sure this implementation is right. Okay, for this polynomial, we collect the coefficients in decreasing order here, and x0 is 3, and we call the Horner that function, and p and d are obtained, and we try to print out. Then result is p at 3 is 19, and p prime at 3 is now 37, is saved in this variable d. Okay, so it's correct implementation. Okay. Now here for this polynomial, use the Newton's method and the Horner's method to find the to implement a code and find an approximate 0 of p near 3. Here. Okay, this is Newton-Horner method. Now, this is quotients of the polynomial, and that is beginning point, and this tolerance and etmax for Newton iteration. Here, and each iteration, Newton iteration, we call, and for given point x, start with now x, x0 is now x, and we call the function Horner and find the function value and derivative value at x. And this is correction term and added to get update the point. And once h in modulus is smaller than tolerance, then we break the iteration. So that is now Newton iteration along with help from Horner's algorithm to get the polynomial value and derivative value. Okay, here a, that is the quotients, and x0 is 3, and tolerance is 10 to the minus 12, and maximum iteration is 1000, and we call Newton-Horner, and here the output is the approximate 0, and we want to see number of iterations, so that here it, number of iteration, is now returned. So we can print out here, and the result is Newton-Horner start with 3, and final point is 2 in 7 iterations. The Newton method converts it in 7 iterations for the tolerance. Now let's see the figure. We start from 3 here. Newton method run here 7 iterations, and then located this 0 quite accurately. For the function, it has two zeros. That is, one is here now, this one, and this one is 2. Okay. In fact, this is quadratic. This is a fourth order polynomial, and there are only 2 real zeros, and there are also 2 complex valued zeros. Okay. Okay, that's the end of section. Thank you.